We're going to do a little review based on that introduction to magnetism that we did yesterday, but we're going to do that in conjunction with the homework that we had last night, which was practice question set number 14. And we start off with question number 1. It says a student uses a bar magnet to pick up a paperclip. If a bar magnet picks up a paperclip, then we know the paperclip must be what? What's that term? What's that word? Yeah, Chase? Right, ferromagnetic. Ferromagnetic material is a material that can become magnetized, right? Now, a bar magnet is a ferromagnetic material as well, but it already is magnetized. And we know that it's magnetized because it has those domains pointing in a similar direction, more or less aligned with each other. Okay, if this is my magnet, and it is a magnet, clearly is a magnet because the domains are aligned, and this is my paperclip, I'm just going to draw it as a bar. It doesn't really matter what shape it is. The domains are pointing in more or less random directions. When I bring this bar magnet nearby this randomized domain paperclip, what happens? Yeah? Was your hand not up? Oh, that's okay. You can answer it anyways. What happens to the domains inside this paperclip? Yeah, they're going to organize and face the same way. Good. In other words, they're going to start aligning themselves. So they're going to be pointing more or less like this. Now, the original magnet had a polarity, a north pole and a south pole. Which end was this, north or south? South. The domains pointed from south to north inside the magnet, right? So this is going to be the south pole, this is going to be the north pole, and that means that this has got to be a south pole and north pole as well, at least temporarily, all right? All right, when I take this magnet away, then a little while later, the magnetic effect is going to slowly disappear in this paperclip, okay? But as long as the magnet is there, hey, this is going to be a magnet. It's going to be a temporary magnet. And it's going to attract because north attracts south. So just like when we had, or almost at least like when we had a charged object and a neutral object, and charged objects attracted neutral objects because of a temporary separation of charge, we would say that magnets attract paperclips because of a temporary alignment of the domains. So what's our answer here? A student uses a bar magnet to pick up a paperclip. The magnet causes an alignment of domains in the paperclip, which results in the paperclip becoming a temporary magnet. Good? Number 2, which of the following diagrams illustrates the magnetic field surrounding a bar magnet? Okay, this one's pretty straightforward. This is literally straight from the notes that we did yesterday, straight from that activity that we did yesterday. We have to remember just one thing here because the shapes are all the same, so we don't even have to distinguish between shapes. We have to remember the definition of the direction of magnetic field. We define the direction of the magnetic field in 2 ways. First way was the way that good. The way that a compass needle moves when placed in the field. What's the second way we define it? Well, a compass needle points which way? No, other way around. Well, it goes from north to south. Yeah, it goes from north to south. So that means that which one's going to be our answer? Well, A has our magnetic field going toward the north. Compass needle doesn't point toward the north. It points towards the south. Magnetic field going towards the north again. C looks like it works. Okay, magnetic field going away from north toward the south. That's the way that a compass needle would point. D almost works, but this little area right here has it going in the wrong direction. So our answer is C for that one. 3, the direction of the magnetic field at point P due to 2 bar magnets. Some people, when they do this question, try to draw some magnetic field surrounding like this, and then it gets a little bit confusing. And technically, you could do that, but it is more confusing. The easiest way to tackle a question like this is look at the magnetic field of each one independent of each other. So we're going to say for the first one here, we'll make it the blue one. We have a magnetic field pointing this way. It's away from north. And for this one, we'll call it the green one. We have a magnetic field pointing this way, toward the south. Now, the reality is the magnetic field doesn't look like what we have drawn on the board right now. It looks like a combination of what we have drawn on the board right now. At that point, point P, the magnetic field is going to be in between the blue and the green, or up and to the right. So even though the magnetic field doesn't look like blue or green, it's easiest if we look at them independently of one another and then combine them, as opposed to trying to draw, magnetic fields going everywhere. So the answer for this one's going to be D. And finally, number 4, here's the good question here. Venn diagram below can be used to compare gravitational, electric, and magnetic fields. We've got our gravitational field here, we've got an electric field here, and we've got our magnetic field here. And we can see some overlap here, right? Number 7 is where all 3 of them overlap. 5 is where just gravity and electric field overlap. 4 is where gravity and magnetic overlap. And 6 is where electric and magnetic overlap. What's 8? Like, not properties of any of them, right? It's not a property of an electric, gravitational, or a magnetic field. So let's look at what we're trying to find here, and then match it up here. Can be directed toward the source. Toward the source. Can you have a gravitational field that's pointing toward the source? Absolutely. It has to be toward the source, right? You got no other option for gravity. It's going to be toward the source. What about the direction of the... Here, let me change that to the gravitational field symbol. What about the electric field? Can it be directed toward the source? Absolutely. It can be directed away from the source as well. It depends upon what kind of source we have. If it's positive, it's away from the source. If it's negative, it's toward the source. So the electric field can absolutely be directed toward the source. What about a magnetic field? Trace? Yeah, absolutely. Magnetic field is away from a north pole and it's toward a south pole. So it can absolutely be toward the source. So we've got all 3 of those, which means it's going to be what? Option 7. Good. Can be directed away from the source. Can gravity be directed away from the source? No. To the best of my knowledge, you can't have gravity acting away from what causes the gravity. It's always got to be towards it. So gravity, no. What about the electric field? Can it be directed away from a producer? Yeah, if it's a positive producer. And what about the magnetic field? Yeah, it's away from a... can be away from a north pole, right? So electric field and magnetic field overlapping, that's going to be option, what is it? Somebody said it? 6, option 6. Good. Now, these are the tough ones, but there's a lesson to be learned in this, a lesson that you've already learned, but sometimes that we forget, aside from the actual concept here, is inversely proportional to the distance squared. Well, G is gm over r squared. That's inversely proportional to the distance squared. The electric field is kq over r squared. That's inversely proportional to the distance squared. What about the magnetic field? We haven't even learned an equation for the magnetic field, right? It is not inversely proportional to the distance squared. How are you supposed to know that? There's a simple answer to that. How are you supposed to know that it's not the answer? Because you haven't learned it. You can always trust me on that. Okay, right now through the diploma exam. Okay, you don't ever have to guess on something, unless you just forget something, right? If you haven't learned that it's the answer, then it's not the answer. Got it? Every once in a while, something pops up like that. Every once in a while, they throw something in there that's like, oh, I haven't seen that. I haven't learned that. Okay, that's fine. They're only going to test us on what we've learned. So that means if they're asking us a question, they're not really testing us on something we haven't learned. They're saying it's not the answer. So the magnetic field wouldn't be the answer right here. It would just be gravity and electric, which would mean it would be option, if I scroll up here, option 5. Is directly proportional to the distance squared. Well, I know that the gravitational field isn't, the electric field isn't, and what about the magnetic field? I don't know. Well, then it can't be, right? If we haven't learned it, then it can't be. So what's our option here? It would be option 8 then. 7, 6, 5, 8 is our answer.